Okay, hello, welcome to chapter 16. This is going to be, the chapter of this is called Electrophilic Attack on Derivatives of Benzene. So it's going to deal with a lot of concepts that you learned from the previous chapters of electrophilic aromatic substitution, so the EAS for short. And this is just a quick review. So you have a benzene compound right here, and then this is one of our reactions that we talked about, and I think I showed a mechanism for this, but this is bromination. So what's going to happen is that this benzene ring is going to react with this bromine molecule, and it's going to have the bromine up here. And um, I could have drawn this bromine anywhere on these carbons because they're all symmetric here, and it would be the same IUPAC name, right, if we were to follow the IUPAC naming, so it doesn't matter. But the main topic and the main goal of this chapter is what happens if they're not all the same carbons? What happens if it's not just this benzene ring? What happens if it's a derivative of benzene, right? So something that is formed from benzene, or something that can be a benzene after it's reacted with something. And this is what we're going to be mainly talking about. And in this chapter, there's going to be a lot of resonance. So if you understand and if you completely understand resonance, you're going to be perfectly fine for this chapter. But if not, it's okay. We're going to go through it again. We're going to go through that today. Okay. So what happens when we just put a methyl group on the top here? You see how if I just put the bromine on, let's call this carbon number 1, carbon number 2, if I put the bromine on carbon number 2, it's not the same as putting a bromine on carbon number 3, and so on with carbon number 4. It's different molecules, right? They're not they're constitutional isomers now. They have the same formula, but they have different structures, and they have different connectivity. And this connectivity leads to different chemistry, right? So again, we have this benzene, but we just added a methyl group on the top, and then we added a bromine. And then, as you know, we could add the group. We could add it either on this carbon, or this carbon with the electrophilic attack, right? We can either have it on this bromine. It wouldn't go the this wouldn't be possible because it's too hindered here. So it would go on this one, this one, this one, and these actually have special names. So this first molecule, if the bromine is one carbon away from the group, again, this is symmetric of this angle right here, right? So this carbon here and this carbon are exactly the same. So it doesn't really matter which way. I decided to go right because I think it's a lot easier, okay? So if it's one carbon away from the carbon with the group, this carbon has the group, it's called ortho, right? Like in orthodontics or whatever. If it's two carbons away, it's called meta. And if it's three carbons away, it's called para, right? And you'll see uh you can like shorten the terms like o comma p, or m, or o dot m, whatever you want, but it's ortho meta para, and I think it just rolls off the tongue like that, ortho meta para. And you get to see like, oh, ortho is carbon number, the one carbon next to the group, and then meta is two carbons, and then para is three carbons, right? So is there going to be a major product here? And if there is, why is that the major product, right? So when you're thinking about this, I only showed you the products. I never showed you all the nitty gritty mechanism stuff, and all these things that you have to consider with like mechanisms. But with this, we're actually going to have to consider it. So let's take a look at the resonance, right? So here I have our benzene molecule with the um uh with the methyl group on the top, and then we have our electrophile, right? This is an electrophilic aromatic attack, right? Substitution, sorry. So what happens if our electrophile goes up to this carbon. If it goes up to this carbon, that means this carbon right here will have a positive charge, right? As noted here with the positive charge. But because we have this double bond here, I'm sorry, my benzenes are disgustingly horrible, but you're gonna have to deal with it. I don't know. Um, I'm an organic chemist. I'm not a artist. So yeah. Okay, so let's the positive charge goes to this carbon, but we have resonance here. So we can resonate it, put the carbon double bond to this carbon, which means this carbon now is going to have the positive charge, right? Boom. And then we have another double bond that we can get up here, which will resonate here. This carbon will now get the double bond, which means this carbon is going to be have our carbocation, right? So let's classify these carbocations, okay? So what type of carbocation is this first one? Well, I see 2 carbons here, so this is a secondary. Pretty good. What about this one? This is also a secondary carbocation, right? There's 2 groups. And then what about this one? This one has 1, 2, 3, so this is a tertiary carbocation. Pretty good, right? So what happens if now, instead of the electrophile going here, I mean here, we have it going to this one, okay? So let's see what happens. If it goes onto this one, the carbocation stays on this carbon, right? And then we have resonance from this carbon, and then we resonate it, then the carbocation goes here, and then we have another resonance here, which is good. And then it goes all the way down here. So again, let's do what we did up top. Let's classify these carbons. So this one is a secondary carbon, right? As you can see, secondary carbocation, pretty good. This is also a secondary carbon, and this is also a secondary carbon. So a little weird. Let's see. If it's added ortho, right? Remember our conventions for naming. There is a resonance with a tertiary carbocation, which is a lot more stable, right? But if it's added meta, it doesn't have a tertiary carbocation, which means it's not going to be as favorable as if we were to add it in the ortho position, right? So let's keep that in mind. There is one more that we have to do, and that is the last one if it was in the para position, right? So if this carbon had if this carbon had the electrophile sticking out, which would make this carbon a carbocation, right? So let's see that. This carbon, we resonate it, right? And then we have this. And then now we also resonate this carbon over here, which means we have this now, right? Super simple. Super simple resonance. Please try to work this out at home. I'm just telling you the main ideas that you should get from this, right? So again, let's classify our carbons, carbocation, sorry. This is a secondary, right? This is a tertiary, and this is a secondary. So let's see what happened here. If our electrophile, if our bromine, right, is added ortho, we have a tertiary carbocation intermediate, right? We have a tertiary carbocation intermediate, even though with resonance, right? So if it's added ortho, we have a tertiary carbocation, which is good. If it's added meta, right, 2 carbons away from this methyl group, we don't have a tertiary carbocation. We only have secondary carbocations. Still good, but remember what's more stable than a secondary carbocation? It's a tertiary carbocation, right? So this is going to be favored. And what if it's added para, our last one? We have 2 secondaries, and then we have a tertiary. So let's recap. If it's added ortho, right? If it's added ortho or para, we have a tertiary carbocation, which is good. But if it's added meta, it only has secondary carbocations. So there is going to be a major and minor product, right? The major product will either be ortho or para because we have a tertiary carbocation intermediate, which makes it more stable than if it were to be added meta. And you will see this where ortho and para have around an 80% yield than meta. And that's how important this resonance is. And the ortho and para, it depends on like where it is. So if you can see, if we add it ortho, there is sort of this steric hindrance right here, right? It's not that big, but it is still there. So it would be more favorable if we added it para, right? You see how these groups are anti to each other. So you don't need to know that. You just have to know that. Well, you do need to know that. Sorry. You have to know that it's going to like ortho and para additions more than it likes meta because of this tertiary carbocation intermediate, right? So a methyl isn't going to be our only group that we have that we might have on this benzene ring, right? There's going to be a ton more, and you learn a lot more groups that can be added on to the benzene ring, right? So let's see how those groups affect where we're gonna add it, either ortho, para, ortho, meta, or para. Okay. So let's see. Let's first define some terms that we're going to use. So one is going to be called an activating group, and these activating groups makes these benzene rings more nucleophilic by resonance or hyperconjugation. Basically, it's saying it's going to make the ring more nucleophilic, which means the reaction will go out faster, right? Remember this reaction? It doesn't go as fast because this benzene ring is not really a good nucleophile, right? And if we make it a good nucleophile, let's say if we add a negative formal charge here, that means it's going to be a better nucleophile, which means it's going to react quicker. Right? So a deactivating group is the exact opposite. It's going to make it less nucleophilic. And it's going to make it less nucleophilic because it's going to add either a positive charge or it's going to take all this density of electrons here, this electron density is going to go to whatever group this is. And you may have heard this, you may have seen this concept before, but imagine if we have like a halogen here, which is very electronegative, right? Let's say we have a fluorine here. It's just going to hog all this electron density up to the fluorine, which means this isn't, well, one, this wasn't as nucleophilic, but now because the fluorine is now hogging all the electrons, it's not going to be, it's going to be less nucleophilic than it was before, which makes this reaction slower, right? So those are just some terms to know. And then I do have a chart here, right? So we have a chart. This is it's a strong activator or a strong deactivator and a mild activator and a mild deactivator. So the difference between strong and mild is how um, just like uh, if it really adds on an actual negative, right? If it's an activator, if it adds on a negative, right? If it adds on a negative formal charge to the ring, or if it just donates some electron density to make it more nucleophilic, right? So it's like either a full or a partial. Think of it like that, where a strong one would fully donate a negative, making it super strong, making it super activated, whereas a mild would just make it like a delta positive or a delta negative, right? Depending if it's activating or deactivating. And then we have here O dash P or M, right? Remember in our previous examples, the ortho and para positions had tertiary carbocation intermediates. So what's going to happen is if you have a group like OH onto your benzene ring, it's going to be activating and it's going to direct whatever you're reacting it with. Let's say you're going to react it with a bromine, right? Br2 with FeBr3, it's going to direct it ortho or para. Whereas if you had a benzene ring with, let's say, this ketone, it's going to deactivate it, making it less nucleophilic, and it's going to direct it in the meta position. So it's going to direct it the second carbon away. And you see, it's really easy to remember how there's only one type of group that makes it meta directing, whereas all the other groups are ortho and para directing because of the stability of the tertiary carbocation. Okay, so I have some examples of how, let's go with OH, of how this is a strongly activating molecule, right? So let's say we have this OH group right here, right? Let me just erase the resonance arrows. So again, OH has I listed it up here as a strong activator, right? It's right here, OH, and it's going to direct the orthopara, but we're just going to focus on the activating part as of now. Remember, activating groups make rings more nucleophilic by resonance or hyperconjugation, right? So let's see here. This oxygen has two lone pairs, right? Which means it can donate its electron density to this ring, right? So there is resonance here. It can come down and form a double bond with this carbon. But if we do that, then this double bond here will have to leave to this carbon, right? And if that happens, we form a double bond, C double O bond with that oxygen, and we put the double bond lone pairs onto this carbon right here. And what does that give the carbon? It gives it a negative formal charge. And as you know, negative formal charges are good nucleophiles, which means it's going to be activating, right? You see how it's donating its electrons to this ring, giving it a full negative charge, which means that it's a strongly activating molecule. That means in an electrophilic aromatic substitution, this is going to happen a lot faster if you were to compare it with something like benzene, just a regular benzene, right? You see how in this, there is no negative charge. Everything is just neutral. But here, since we have this negative charge, it's going to react faster. And then let's see now our strongly deactivating molecule of ketone, right? So again, so what's going to happen here is that ketone will take electron density away from the ring, making the ring less nucleophilic. How is it going to do that? Well, there is going to be resonance here. You see how this ketone here has a double bond, C double bonded O. If this bond goes up to the oxygen when it wants it, that means this carbon here will get a positive charge, right? But we have a carbon right next to it that can donate its electron density. So we go up here. If that happens, then we form a double bond here, right? This oxygen has now a negative charge, but look what happens to the ring. The ring now has a full positive charge. That's really bad because one, this double bond ring is not nucleophilic at all. That means it's not as nucleophilic as other molecules, which means it's going to react slowly. But now, once you add this positive charge, it's not even going to react. It's not even going to attack something. It's going to be attacked, right? So that means it's going to deactivate this ring, making it less nucleophilic, which means it's going to be slower than if we compared it to a regular benzene, right? See how this is neutral, but now this is a positive, which means it's deactivated. It's not nucleophilic anymore compared to a full negative, right? So those are just some examples of such groups, right? So now let's put all that into consideration and do some practice problems, right? So I do have a few practice problems that I'll show you. So first, we have a benzene ring with this weird isopropyl group, right? And we're going to treat it in HNO3 under acidic conditions of sulfuric acid. If you remember your reactions to know, this is called nitration. So we are going to put an NO2 group onto a benzene ring. So it looks like that, right? So which carbon are we going to put it on? Well, let's first number the carbon. So which carbon has the substituent? It's this carbon, right? We can go either left or right. It doesn't matter because it's symmetric. I'm going to go right, okay? So one carbon away, this is ortho, right? Two carbons away is meta. Three carbons away is para, right? So let's take a look at this. Is this going to direct it ortho para, or is this going to direct it meta, right? Is this a strong activator, or is this an activator or a deactivator? Well, if you think about it without looking at the chart that I gave you up top, this is actually going to donate electron density to this benzene ring through hyperconjugation, which makes this a strong activator. And we know strong activators direct it ortho or para, right? And let's just go up and check if we're right. That is a methyl chain, right? An alkyl chain, CH3. And we were right. It's a mild activator, which means it directs it ortho para. So let's see that. Let's add the NO2 ortho first. So we have, and then this NO2 is going to be right here, right? And then we can add it para as well, or orthometa para. So out of these two, which one do you think will be the major product, right? I did go over this slightly at the beginning, but if we think about it of steric hindrance, this is going to be very hindered, right? You see how this um, nitrogen group is close to this isopropyl group, which means there's a lot of hindrance here. This will happen more than it will with the meta, but this is just going to be a little bit slower. It's going to be a minor product. And if we're talking around the ranges of like percentages, this might be 30%, but this will be 70%, right? You see how um, the group is added further away from the uh, bulky isopropyl chain, right? But if you add these two, you're completely correct. This is just the minor, and then this is the major, right? So pretty easy. Let's go through what we did again. We identified which carbon has our substituent, and it's this carbon. We then named ortho meta para positions. One is ortho, two is meta, three is para, right? And then from that, we looked at what we're going to do to the reaction. In this case, it's going to be a nitration. And because it's going to be a nitration, we know that NO2, oh, ah, we know that NO2, sorry, I think I need to reshare. But we know that NO2 is going to be added to the chain instead of we know that NO2 is going to be added to the chain, and we can add it either ortho or para. Okay, let me just uh, share my screen again. Okay, hold on. Okay, I think that's better. Yeah, that's a lot better. Oh, I didn't even realize I, sorry. But yeah, so uh, yeah, okay. So let's move on now. And then now we have slightly a little bit different. We added another methyl chain here, but we already have a methyl chain of here, right? Oh, we already have this methyl chain, but we just added another methyl chain, okay? So don't panic. Let's just go through what we did before. Let's number this. This is ortho, meta, para, right? So we know it's not, so then let's go to this side. Let's go um, ortho, meta, para, right? And it's going to be the same the other way around as well. So which one takes charge? Which one is going to direct it in which way, right? So we labeled our ortho meta paras, ortho meta, oops. ortho meta para, and then from this side is ortho meta para. So we know immediately that it's not going to add it in the para position, right? Because it's just too bulky and it's too substituted, which means it's not going to add it to those positions. Oh shoot, sorry, this is supposed to be not this one. My bad, my bad. All right, I just got so thrown off by that. I'm so sorry. Boom. It's supposed to be like that, okay? So again, let's number it. So this is ortho meta para, right? And I'll do purple, where this is ortho meta para, right? So let's see here. We have we have this, which is competing for ortho and para, and we also have para here, and we have ortho here, right? So it's either going to add it ortho or para, right? Because these are going to be groups that are ortho para directing. So we can cross out the metas, right? So let's add these all, and let's see what happens. Let's first add it ortho to this group right here, NO2. And then let's add it ortho and para for both, which is right here. And then lastly, let's add it para for the alkyl group on the right side. And then we have, oops, meta para, okay? So let's think about this in terms of steric hindrance, right? So we figured out it's supposed to add either ortho or para, and then we figured out that there are three ways that this molecule can be drawn, that um, this product can be achieved, right? So let's look at this position right here. The NO2 group is being added in the middle of these two bulky side chains. In this case, it's added onto somewhat rather bulkier, not as bulky as this isopropyl group, but it's added into a group that has a methyl, and in this case, it's added to the group right next to the isopropyl chain, right? So if you're taking a look at these three products, in my mind, oops, this is going to be the one that does not happen and might not happen because of the steric hindrance, right? If it does happen, it might be at like 1% or 5%, right? Very, very small. And to be honest with you, we don't have concrete evidence as to which one of these two will happen first, which one will be the major or which one will be the minor. But we can guess and we can hypothesize, make an educated guess that this one will probably be the major and this one will probably be the minor product, right? Because of the fact that this is being added next to a group that's less bulky than this isopropyl group, right? Whereas this one, it's added onto next to this isopropyl group, which makes it more unstable or with more hindrance, right? So in that case, this one will probably be the major and this one will probably be the minor, right? So, and then let's move on to this example. So we have a different scenario now. We have a methyl group up top and we have a hydroxyl group on the bottom. And in this case, we're doing a bromination, right? So this is the bromination, right? And through bromination, um, what's gonna happen is we're gonna add a BR onto one of the side chains, right? So let's see what happens. Let's number the carbons from this side. Ortho meta para. It's the same thing for the other side. And then let's do it on this side. Ortho meta para, right? So in this case, which one is it going to do? And it can also do it ortho meta para on this side as well. So yeah. So which one is it going to do? So in this case, we have a methyl group, which is ortho para directing, right? and we have an OH group that adds to this electron density, makes this a negative, right, in one of the carbons, and it's ortho para directing. So in this case, we have two ortho para directors, but which one is stronger, right? And if you look, this is just strong by hyperconjugation. This is just going to add by hyperconjugation, right? But this hydroxyl group is going to add a fully negative charge, right? You remember we drew some resonance structure where this hydrogen, oxygen gave one of the carbons a negative charge. So that means this hydroxyl group is going to be the stronger director, which means it's going to direct it ortho or para from the position of the hydroxyl group, right? So from this position, we're going to add it either ortho or para. We can't add a para because there's hindrance here, so we have to add it ortho, right? So we can add it ortho. OH, and then right here. And then also, it can also go to the other side, like that, right? So we learned how strong of a director that oxygen is, right? And then oxygen beats out this methyl group, which means it's going to direct it from the side that it's on, ortho or para. And then just a couple things to note. There is going to be a synthesis question, and I believe that this is very important to know when you're doing this chapter. So it's a synthesis. Um, so I just wanted to tell you that order matters, right? Because we have um, this ordering now, we um, the order that you add on these groups will matter, right? Because bromine is an orthopara director, but this nitro group is a meta director. So it matters where you put it on, right? It matters um, where you want to, um, how you do it, and which order you do it in, right? So let's say we want this product, right? We want the bromine and we want the nitro group that's meta to the bromine, right? So let's see. Let's see we do a bromination first, right? Followed by a nitration. So first we prepare this Br2 under FeBr3, and then it just adds on to whatever carbon, this one, I'll do this carbon up top, right? And then after this, we are going to react it with, we want the NO2, so we're going to do HNO3 under H2SO4. And then we have to be careful here. Now we have a substituent, right? Bromine is an ortho para director, right? So it's either going to add it to this carbon or this carbon. And we know that from previous examples, it's going to be more major if we add it onto the para position, right? So let's add it onto the para position and then Br. Okay, I'm not gonna write. I just did what we just focused on, right? So if my pointer doesn't work, it's fine. I'm just gonna go through it. So the first reaction, we we wanted to synthesize that molecule up top, right? We wanted to synthesize that from a benzene ring, right? So first, let's say we did the bromination and then nitration first, right? Let's say we added the bromine first and then the nitrogen group. So if we did that, we did the first one, what we did bromine, bromination, and then the bromine is now at the top, right? And bromine is an orthopara director, but we learned from previous examples that it's better to add it para in most situations because there's less hindrance, right? And if you see the nitrogen, the product at the top, what we wanted versus the product what we have here is not the same. This carbon with the nitrogen group is 1, 2, 3 carbons away from the carbon with the bromine group. But this carbon with the nitrogen group up top right here is 1, 2. So that's not the same. And that matters because these are not the same molecules. Because we added the bromine first. The bromine is an ortho para director. But what happens if we did it the other way around? If we added the nitrogen group first and then the bromine. So let's see what happens. We did the nitration first, we just reversed these steps. But the difference now is NO2 is a meta director. It's going to direct it to 2 carbons away. And that is exactly what we want versus to this product. So be careful with your products, be careful with your reactants, and I hope that you found this helpful. I'm sorry for the technical issues. I will find a better way to do this, but I hope you learned something and I hope you have a good one.